Okay, so visual acuity, I think part three. I don't know. Visual acuity, it will take 10 parts. Let's see. Start here with a small topic. I think today's presentation is also uh, 7 8 slide longer. So today I'm going to talk about the why diffraction limits the vision. Okay, and definitely read it criteria. So diffraction limits the vision. What is diffraction? Diffraction, basically we know that whenever light or any wave hits any aperture, which is comparable to the wavelength of light or wavelength of sound or anything, or at that time it bends. And the diffraction, the classical thing in our visual system, we consider diffraction as wave nature, and it explains why image object and image, definitely image degraded what in, if even if a geometrically perfect optical system. So diffraction effects is related to wave nature of light, which often ignored in a geometrical optics, because in geometrical optics we talk about wave focus, defocus, but we don't talk about diffraction. Okay, so when we put the input, the detected image is, see, in this case we can even detect there is a four at least bars, but in this case can we detect it? No, because it's look like a chunk of whatever, but it's very difficult to detect exactly how many bars are there, isn't it? That is resolution. Okay, so diffraction limited system. So many times you see in your textbooks or other standard books, diffraction limited system. What do you mean by diffraction limited system? Okay, so diffraction limited describes the image system that produce fine images of same quality as instrument theoretical limit set by diffraction. Okay, whenever we set the diffraction and we produce the fine image quality instrumental theoretical limit, that limit is called diffraction limited system. So we know our eye is also an instrument, optical instrument. We compare eye with sometimes definitely with camera. So we want to know the diffraction limited imagery system and its theoretical limit, isn't it? That's what Rayleigh's criteria, isn't it? So what happens when point object passes through the optical system and it produces image? We know it will never produce ideal image. Is it possible? It is not at all. There is aberration, there is focus and defocus, and there is definitely diffraction. So what happens if we consider diffraction? So the smallest extent of an image from the distance point object has intensity distribution pattern known as eridix. Why we call eridix? Eridix means it's not a point. Okay, point object do not produce point image, it produce eridix. And what do you mean by eridix? Eridix mean by central brighter and darker and slightly brighter and darker, something like that. Can you see? Central low, this is central brighter, and then darker, this is dark, isn't it? Trough is dark, and another bright, another dark, another bright, another dark, another bright. So that's what pattern forms, and that pattern is known as iridis. So we can calculate that iridis, the size of the iridix, isn't it? So the angular radius of the first zero in a medium in radiant is can be calculated by this formula. This formula you will see a lot of time in your visual acuity chapter. Okay, 1.22 lambda divided by n, refractive index of image space, definitely 1.336, and the diameter of what? Diameter of pupil, because in our eye it's pupil. Okay, so in that case, if object is this, image is iridescent, so which center is brighter, and the center, that is zeroth, zero, first zero in medium. So angular radius formed by this can be calculated by this formula, that is 1.22 lambda wavelength n into d. Okay, so what is Rayleigh criteria? So in Rayleigh criteria is based on the diffraction and iridice. Okay, there are other criteria too, like Nyquist theory and other things. We will discuss later on about they are basis they are going to based on the spacing between the photoreceptor and uh, macula. But let we will cover it in another video. But what is Rayleigh's criteria? Okay, at the time of resolution, there will be resolution only. The central bright maximum of one iridis must coincide with the first minimum of the other. So this is the line we want to just remember in our examination, and we just go in our examination and we vomit out. But we have to understand what it means really, not just vomit out. In another sense, this second line is another sense. The first line is exactly correct. Okay, we have to understand second line is the peak to peak separation of the two airy disk formation is at least, just remember this word, it's at least equal to the radius of the central airy lobe. Okay, so this is another way of thinking, which is very simple, easy. Let me go to the first. At the limit of resolution, the central bright maximum of one iris must coincide with the first minimum. What is first minimum? First minimum dark of the other. See, there is 2 point. Okay, wait, there is 2 point, and 2 point forms two peak and bright, something like that, isn't it? So this peak must fall here if they are close. If they are this much is separated, then obviously there is resolvable. Okay, but if they are close together, they are not resolvable. It means this. See, one object definitely forms the eridix. Two objects which is close together cannot be resolved. Can you resolve it? No. Cannot resolve because one peak falls under the another peaks, not here. It should fall here, isn't it? For minimum resolution, it should fall here. First minima of the another. First, this is another eridix. This is another eridix. So it must fall under this or greater. Definitely, the separation between two eridix minimum is this, but can be greater obviously. The minimum, it must fall, the peak of the another should fall under the dark first dark of another. Peak of one iris must fall first dark of another, isn't it? I'm getting the concept. Peak of one iris must fall minimum, at minimum, not just must, at minimum fall first dark of another. And then if they align, at that minimum resolution can happen. Okay, at that point minimum resolution can happen. See, first case is the iridix. Second case, we cannot dissociate between, there is two stimuli, there it look like there is only one stimuli, and then third part we can resolve the pattern, isn't it? So that's what mean by resolution. We can say there are two things, isn't it? So if you put everything, let's take an example. If we put things, let's take an example. Lambda is 550 nanometer, which is peak sensitivity. Index is definitely 1.336, which is image space. And let's consider pupil is 2 mm. At that condition, we found minimum angle of resolution. Diffraction limit is 0.86. That's why in a round one we take 1 minute of arc, isn't it? 1 minute of arc is a resolution. So this minimum angle of resolution is gained by the formula, diffraction limited formula, which is another way we can call it Rayleigh's criteria. Okay, but we know that what happens if we change lambda. Can you guess? See, mar. What do you mean by mar? If lambda is increases, mar also increases, isn't it? It's directly proportional. What do you mean by mar increases? Mar increases means decrease in vision, isn't it? Visual acuity. The lesser the mar, better it is. So at the same time, can you see mar is inversely proportional to the uh, pupil diameter, isn't it? As the diameter increases, mar decreases, which means better visual acuity because visual acuity is 1 by mar, isn't it? So same thing happens here. See in this picture, as the pupil diameter increases, minimum angle of resolution decreases, isn't it? Which means the better vision. But we we have to think another way. It's not just one variable, that the diameter of pupil and the diffraction. There are other variables too, like example aberration. And in case of aberration, as the diameter of the pupil increases, aberration increases, and as aberration increases, visual acuity decreases. That's why it's a sweet balance between two and many other factors, isn't it? Like the density of cone and the spacing of the cone. There are a lot of things that are going to happen there. So it's not just about diffraction and we simply think as the pupil dilate, visual acuity improves. No, that's not the case. But in one way, if we are considering only diffraction, then that's the case. If pupil increases, pupil size increases, diffract, and based on diffraction, based on Rayleigh criteria, visual acuity must improve. But it's not just a case we only consider diffraction. Okay, fine. So finally, we understand iridescence. Second, we understand diffraction and diffraction limited system, and we understand this formula, isn't it? 1.22 and d, and how we consider these two. I don't talk about n because it's impossible to change n. Is it possible? No, it's not. It's not possible. It means n is definitely 1.33. So what happen if these two conditions change, and what is exactly Rayleigh criteria? You must understand these things. Okay, so finally, these are the only book I have taken as a reference, my favorite book from Professor Dr. George Asimelis. Okay, I will come with the third video. I think aberration is the main, aberration of the visual acuity is the main chapter. Okay, bis dann, tschüss.